Hi, my name is Sofia Wanda Vasquez. I'm a master's student in applied physics at the Universidad de AFI in Colombia, and today I will present you an accurate and fast-paced computation of dynamic samples in digital holographic microscopy. So, we first need to understand what is digital holographic microscopy. The DHM is an interferometric recording technique in which we have a object wave that carries on all the information of a specimen, like for example in this case a red blood cell, and a reference wave. These two waves they interfere with each other. We record this interference pattern with a digital camera. When we have this register that's called hologram, we can retrieve the complex field of our sample, and we don't require for staining the sample in order to recover all the information that we are interested in. So this is a great advantage over other microscopy, traditional microscopy techniques. Like for example, in biology, they usually need to stain this. But also when we're working under off-axis configuration, we have a single shot technique, which is very desirable when we're talking about dynamic phenomena. So when we talk about phase and phase map compensation, we have to keep in mind that the less phase jumps we have in our compensation, the better the compensation is. What this means, please see the three images that I present you here. Each one of them, the only difference that they have between them is the phase, the digital reference wave that we created for the compensation. So this validates our statement that when we, or what we aim to achieve is a plane phase, homogeneous background, as in the last um, phase map that I present you over here. So yeah, that's our main goal with this algorithm. So let's keep in mind that and let's continue. So how do we perform this compensation, which is the state of the art? So on one hand, we have the grid search algorithms that the main disadvantage of these algorithms is the high computational complexity that they require for their performance. This means that usually you wouldn't be able to run them over a personal computer. You'll need like a very good computational station and to perform these compensations. But the advantage that they present is the robustness. They can always find the best compensation possible, uh, but you need to give them time. Sometimes you don't have that time to perform the algorithm because you have a dynamic sample or so. Then the heuristic algorithms try to fix that problem. The main disadvantage of this type of algorithms is that they might present a background stability when they having time series to compensate, or the local minimum problem in which it's pretty common when you don't have a well-behaved function. So yeah, but uh, they are really fast algorithms for this type of task. So and when we study this state of art, we try to propose a new method called the semi-heuristic phase compensation algorithm that takes the best of the previous two methods that I just exposed. And so we try to create a robust algorithm that is also pretty quick. That's why it's semi-heuristic. And let's talk about a little more. So which are the requirements for this algorithm to perform outlook compensation of the phase map? Well, first, we need that our system is working on telecentric mode. This means that the tube length is placed in the back focal length of our microscope objective, right? So the lens tube is placed between the microscope objective and the camera. This configuration will ensure us that we're working under diffraction limited, and also it compensates for the additional spherical aberration that appears due to the microscope objective. But how do we know that our system is under telecentric mode? In the two spectrums that I'm showing you over here, you can see that the orange one is pretty spread over the space, right? Whereas the green one, the one that is under telecentric mode, is pretty narrow. That's what we're searching, that our spectrum is as narrow as possible because that ensures us that our system is working under telecentric mode. All right. Now, the second requirement of our system, so the SHPC can work properly, is the off-axis configuration. Under this type of configuration, you just have to tilt the last beam splitter of the system, the one right before our camera. So in the Fourier transform of our holograms, we will have this type of configuration in which the three diffraction orders of our spectrum are completely separate. There's no overlap between them, so we can perform easy spatial filtering so to recover our information, the one from the sample. So the core of our proposal is to find the correct spatial frequencies that lead to the best compensation. This is the equation that models the digital reference that we create for each hologram. As you can see, this among others, it depends on the tilting angles between the interfering wavefronts. That also depends on those carrier frequencies that I just mentioned. So how do we find it without needing of knowing the physical angle? So we can estimate it. We first have to find the brightest pixel inside the +1 diffraction order of our power spectrum of the hologram. So in it, we mark it, and then we create a mesh around it with a step less of a pixel, smaller than a pixel. And then we start performing several compensations, as you can see, which with each of the points within this mesh. Here we're searching for the compensation that has the less phase jumps, but it does not necessarily mean that is the best of all. So once we find it, we perform another search, this time smaller, as you can see in the green grid. And we perform this process all over again until there's no better compensation than the central one, the big circles that we mark here, the pink ones. And as you can see, then we can make or mark like a path that we follow for this compensation. So this is why we call it semi-heuristic, because even though we're performing several search grids, there are like guided ones, so we can find easily and faster the carrier special frequency that we're looking for. So let's see how did we validated this method. So the first one metric is the mean slope metric, in which we take four slopes over the face image. Why? Because we know that if we're performing correctly, we will obtain flat face maps. Therefore, our mean slope must be around zero, and we repeat this process over the stack of holograms that we have. The second metric we use is the compensation times over a personal computer, because we need to know how much does it take to compensate each image. So let's keep going to the experimental results. This first one is a video of red blood cells that are compensated at 4 frames per second. As you can see in this first graphic, we're having a mean slope of in the order of the milliradians, which is approximate zero. So we can conclude that we are having a flat compensation, which is pretty good. And when we're talking about the compensation times, we are performing at around 0.3 seconds, which are the 4 frames per second, which is uh, it's not real time, but it's pretty good in terms of uh, stability and this threshold between stability and fastness. This second experiment that we perform, we're tracking a single sperm cell, as you can see here. This compensation is made at 6 frames per second, and also the mean slope here is even smaller than the milliradians, and our compensation is a little bit faster this time. It was around 0.2 seconds. So we can conclude that our method really works on biological cells. So in summary, this study empirically validates an accurate and stable phase compensation algorithm using two holographic videos of one of human red blood cells and human sperm. The reconstruction performance has been measured using the mean slope over the face map images as I just presented you. The results demonstrate then that the proposed algorithm is accurate over a flat face map and with fully compensated face measurement over the whole field view of our camera, and it's fast up to 6 frames per second in this whole field view. If you're interested in the code that we use in this method, you can find it by scanning this QR code. There you will you'll be led to the GitHub page that we create for it. So finally, I want to thanks to all the parts that has been involved in here, all the entities, and also to my advisors, Dr. Douglas and Dr. Trujillo. Thank you very much. And also thank you for your attention. If you have any question about the method or something else, you can write me to that email that I just give you here. And also remember to scan the QR code. Thank you very much.